Hello there. In today's lessons, we're going to talk about, in general, DC circuits, or at least we're going to do an introduction to it. DC stands for direct current. So I have represented in here a battery, connecting wires, a switch key, and a light bulb. The computer simulation I'm showing here on the right is basically this electric circuit here. In schematics, we have the battery represented by two parallel bars, the longer one representing the positive pole. So here is the positive, and the shorter line represents the negative pole. So positive and then negative. The connecting wires are represented by these solid lines. The switch key is this arrow that can close and open, and then we have the light bulb. Well, with the switch key open, the light bulb does not work. But once we close the switch key, once I close the switch key in here, we can see from the computer simulation that the light bulb would actually start shining. So it will start working. Okay, so closing the switch key will make my electric circuit work. One thing we need to keep very serious in mind is this. The electric field, the electric circuit is only work if there is a loop connecting the positive pole, goes through my equipment and comes back to the negative pole. If I disconnect in any point, like we can see on the computer simulation, it doesn't matter where I disconnect the circuit, it stops working. In order to better understand what happens when the switch key is closed and my electric circuit starts working, let's see this representation here. I'm showing here a zoom in on one portion of the connecting wire. Okay, that's just what I'm doing. And I'm representing here some of the atoms of the grid that makes this material. That could be a copper field, for example. And with the key open, we know that this wire is made out of conductors, is a conductor, and the conductors have free electrons that move around, are free to move, and those are the electrons that will actually conduct electricity. I'm going to represent at this point just one such free electron. So it could be moving like this. Okay, here's my electron. It bounces, comes back here, bounces there, then moves here, bounces, comes back, goes up, comes back. But at the end of the day, this one electron here has a net displacement, delta R, of 0. In trying to build a mechanical analogy to it, let's consider that pinball table. You know, the game is a table that is slanted down. Okay, it has a bunch of obstacles and lights and stuff, and then you pull one ball on it, and the ball comes down in obstacles and you have controls. Okay, and I'm adding a quick picture to help you visualize that. So if my pinball table is horizontal, which of course in the game would not truly work, and I just got a ball in here and pushed, this ball would be bouncing back and forth between the obstacles, but would have no dominant direction to go. When we close the key, we established an electric field inside of my wire. Okay, so closing the circuit is going to create an electric field inside of the wire. Let's say that this electric field is, I'm taking now a portion down here perhaps, and so the electric field is going to be to the left. Well, when I have an electric field to the left, that one electron of my example would now feel a force to the right. So as it's bouncing, this one electron is going to bounce, come back, bounce there, come back, bounce, back, and bounce. It now has a net displacement to the right, because when this electron is being pulled to the left, it's kind of being slowed down by the electric force, by the electric field. And then when it's pushed to the right, it's actually accelerated by the electric field. And then it slows down, accelerates, slows down, accelerates. It has a net motion to the right. On my pinball table example, my ball would now actually go down, bounce back up, but it slows down, and then goes down, and then bounces and goes down, and so on. So now I have a net motion of those electrons. Okay? So now we establish what we're going to call an electric current, which is a net motion of electrons in the direction opposite to the electric field. Let's be very careful with this here now. The computer simulation is showing us now the actual motion of electrons. And those electrons are moving against the electric field from the negative pole to the positive pole. So this here is the direction of what we're going to call real current, and we're going to use the symbol, the letter I, to represent intensity of current. Okay, so that's the real current. When people first defined electric current, they did not really know that the electrons were the ones moving, and so they just assumed a current of positive charge carriers moving in the direction of the electric field. And those positive charge carriers, we still use today the idea of conventional current, which we can see in the computer simulation, okay, of positive charges moving in the direction of the electric field, or from the high potential to the low potential. And as a practical matter, there is no difference between the real current of negatives in one direction or the positive currents in the opposite direction, but for one effect that we're going to discuss in the future. After talking about why this intensity of current is established, how it is, and its direction of motion, we need to define the intensity of current. So we're going to consider again our copper, a wire, a cross-section region of it, a point where I made a cross-section, and a region where there is a chunk of charge that is moving on my example to the right. This is not a vector charge, please. It's just showing that they're moving to the right. And after a certain time, delta t, after a time delta t, so this here is at a time t naught, at a time t naught plus delta t, that chunk of charge would have passed by my cross-section area. Okay? And we define then the intensity of current, I, as being this chunk of charge that crosses that cross-section area divided by the time it took for it to cross. In terms of units, this is going to be given in Coulomb per second. And Coulomb per second receives a special name, ampere. We represent an ampere by a capital letter A, and in the United States, people say a lot amps. I'm going to say a current of 2 amps, a current of 3 amps, or something like that. And that current of 2 or 3 amps just means that for every 1 second that my current is flowing, I have 1 coulomb of charge or 2 coulombs of charge passing by a cross-section area. If I have an electric circuit, electric switch on my wall over here, and I'm using this to control a light bulb that is a couple hundred meters away from me, when I turn the switch on, that light bulb will lit almost immediately. When I turn it off, the light bulb lit almost immediately. One could think that the electrons are going to move really, really fast, but that's not the case. What happens is that when I turn the switch key, I kind of tilt my pinball table a little bit, or I create this electric field inside. And this makes all of those electrons start moving almost at the same time. All electrons through the wire have a tendency to start moving at the same time. Now, notice that when they move, and this bouncing back and forth represented before, their net motion is really, really small. So we call that drift velocity of the electron, and for now it suffices to say that it is a very small velocity, and if my memory doesn't fail me, is at the order of millimeters per second. Let's now talk about the concept of electric resistance. Remember what we just discussed when we talk about the motion of those free electrons inside of the wire. Remember this, those atoms are really far away from each other. Remember that matter is basically empty space. But these atoms, they are vibrating because they have a certain temperature, and temperature is a measurement of the random vibration of those atoms and molecules. Well, as the electrons are moving through, they collide against those atoms. And those collisions actually represent a resistance to the flow of electrons. One example I talk to my students to try to visualize this is if I try to take the class, the whole group, from one end of the hallway, from classroom 1, to the other end of the hallway, classroom 2, during class time, when the hallway is empty, we all can just freely flow without problem. We all just would go, the 20, 25 of us, would just go from one end to the other in a couple seconds. But if I try to do the same thing during transition time, where there is a bunch of people, here, moving around, opening their lockers and backpacks, etc., it's going to be a lot harder for us to go through. We're going to be bumping on each other, we're going to be stopping, going around, and it's going to take us longer to flow. Okay? So these collisions, they represent some resistance to the flow of electrons. And the more these atoms vibrate, the more things are happening in here, more of this resistance is going to be offered. So here it brings us to the idea of electric resistance. I'm representing at this point a piece of a circuit. So these here would be my connective wires, and this squiggly line represents for us, in general, an electric resistance. Some people would also represent that electric resistance by a box, just a little box like this here. But I'm going to stick to the squiggly line. Okay, so this electric resistance could be any kind of electric equipment. It could be a toaster, a TV, an air conditioning, even a light bulb. It could be anything. Well, when I connect this here to a battery, I'm going to establish a voltage across. And voltage actually is a difference in potential. So delta V is V of A minus V of B. Okay, point A and B. I'm going to establish a voltage. And that voltage will actually then produce an electric current, which right now I'm going to stick with the conventional current. And we define electric resistance R as being the ratio between the voltage applied, which can be understood as a pressure to push electrons through, divided by the current that I get, which is the charge my response. Okay? In terms of units, this is then defined as volts per amp. But a volt per amp is called an ohm. Okay? The symbol for ohm is a capital omega, which many of my students usually call a horseshoe. Although we define resistance this way, I prefer to use the equation written this way. Delta V equals IR. I think is more useful this way. Or delta V equals RI. let's now talk a little bit further about electric resistance. So the first thing, let's go back to our equation. Resistance is voltage over current, or voltage equals resistance multiplied by current. First thing I would like to discuss is the effect that temperature has in electric resistance. The thing is that when I change the temperature of the wire, I'm going to change the vibration of the atoms of the grid. And changing that vibration will change the way the electrons that are trying to flow collide against those atoms. Depending on the material, I may also release more free electrons. Okay, so temperature affects the resistance. And for most of the materials we will study, an increase in electric temperature will actually represent an increase in electric resistance. Now, we need to discuss another factors that affect electric resistance, which are going to be called or will come up producing what is known as Ohm's second law. I will discuss the first law later. So Ohm's second law. So Ohm's second law will tell us how the geometrical form of my electrical resistance, of my wire, my material, will affect electric resistance. So let's first imagine in here that I have a wire of length L and cross-section area A. Okay, so the length L tells me just how long it is, and the cross-section area tells me how thick it is. Small cross-section area, large cross-section area. Well, first let's see the relationship with length. If I increase the length of the wire, and then I try to flow current through it, each electron that is passing by will now have, for example, if I double the length, twice as many collisions until it gets to the other side. If I triple the length, 3 times as many collisions. So increasing the length increases the resistance for charge to flow in a direct proportional way. So we can say that electric resistance is directly proportional to the length of the wire. Now, changing the cross-section area will change the thickness of the wire. I could reason that if I double the cross-section area, for example, is as if I was actually placing 2 wires side by side. So now my electric charge has twice the free space to go through, which will produce a decrease in electric resistance. If I do 3 times the wire, the cross-section area, is as if I now had 3 equal lanes to let the charge flow through, and that then make my electric resistance decrease. And what we have is that electric resistance is inversely proportional to the cross-section area. If I put now those 2 results together, I have that electric resistance is going to be proportional to L over A. And we know that if it's proportional, I can then write that electric resistance is a constant of proportionality, L over A. This constant proportionality we're going to call now resistivity of the material, electric resistivity. And we're going to represent this by rho, okay, a Greek letter. And once I plug rho inside, electric resistance then is going to be given by rho L over A. And this is Ohm's second law, written in an algebra-based form, let's put it this way. In terms of units, if I solve this for rho, rho is going to be R A over L, and then that would have units of ohm, cross-sectional area in international units is meter squared, divided by meter. If I cancel these 2 out, I can see that rho is given in ohms times meter. But since in many practical situations, wires would have millimeter squared, typical, cross-section areas and several meters in length, is also common to see rho given in ohms millimeter squared per meter. Now, notice one thing, please. This equation is addressing the electric resistance as a function of the geometric shape. But we have already seen that temperature affects resistance, which really means that this constant of proportionality, rho, the resistivity of the material, is a function of the material. It will depend on every material. It depends on the number of free electrons and how they interact with the grid. But it is also a function of temperature. And for most materials, as temperature increases, rho will increase, thus impacting electric resistance. Let's now talk about Ohm's first law. So I'm going to write again my definition of electric resistance this way. Delta V equals Ri. So what Ohm's first law states is that basically that some materials will have a electric resistance that does not change if voltage changes. Okay? So if I change the voltage for some materials, the resistance will not change. Basically, that's the idea. Notice, please, that this here is implied that temperature remains constant. That temperature remains constant. Because if temperature changes, then the whole thing is going to change. Now, why I prefer to write it this way is because if electric resistance does not change, what this is really telling me is that the voltage is going to be directly proportional to the intensity of current, or vice versa. So if I plot a voltage versus current graph, I expect this here to be a straight line, and the slope of this graph should give me the electric resistance. And materials that follow this behavior, that have this behavior, are also called ohmic materials. Now, materials that do not follow this behavior, which would be the non-ohmic materials, their typical voltage versus current graph could be, for example, either something like this, showing an electric resistance that increases as voltage is increased, or maybe something like this, showing a voltage that is decreasing as, a resistance that decreases as voltage increases. Okay? So basically, this is what Ohm's first law says. In this computer simulation, I am just showing again my electric circuit working, and we see the light bulb shining. And if the light bulb is shining, is because somehow energy is being delivered to the light bulb. Okay? Notice that when I establish an electric circuit, my objective is to deliver energy to my system. It's not really to make electrons move around. Okay? I have electrons everywhere. I have no interest in making electrons move. Actually, on this other simulation, now we have an AC circuit. And AC circuit stands for alternating current, where the current just moves back and forth. As you guys can see, on this simulation, the electrons even don't go anywhere. But I'm still delivering energy to my equipment. Okay? So now let's talk about a balance of energy. When I connect my electric circuit, I'm going to have an energy, electric potential energy, that is being established by the battery or by my power supply. That electric potential energy will then accelerate those electrons, converting electric potential energy into kinetic energy. Those electrons then will, in a basic situation of just heaters, they will collide against the atoms of the material, and in that collision, which is basically an elastic collision, they will transfer energy to the material. Okay? The material that I'm talking about is my filament of my heater, my toaster, my light bulb, and those atoms, when they receive the energy from the electrons, they increase their vibration, increasing temperature. Depending on the system, they got the point where they start glowing, and that's actually how I get light on an incandescent light bulb. So you see that what I'm doing at the end of the day is getting electric potential energy transferred into kinetic energy of the charge, and that then is transferred to my electric device, my equipment. As we always do, electric energy, if I want to calculate how much energy is being delivered, I'm going to talk about work. And then we have that the work done by the electric force as that charge moves around is going to be basically then the product as a concept of the electric force on the electrons multiplied by the displacement of them. Okay? And this here is just a general concept, general idea. The thing is that when I'm talking about an electric circuit, electric force and displacement of electrons is not exactly convenient. That's not something that I can easily measure in an electric circuit. What I can more easily measure are things like voltage, current, and resistance. So I need to try to express this here in other terms. And the first thing I'm going to remember is that voltage between 2 points, or the difference in electric potential between 2 points, is by definition the electric force, sorry, the work done by the electric force divided by the charge I'm moving around. Okay? Let's remember this quickly, that 1 volt is 1 joule per coulomb. So when I have my battery on the circuit, if that is a 12-volt battery, just means that for every 1 coulomb of charge that is moved from one end of the battery to the other end, the battery is delivering 12 joules of energy. That's the idea of voltage. But then there is another thing. For most electric circuits, the amount of energy that they spend is not really what matters for me, but how fast it does. When I set up a light bulb, yes, of course, it is important how much energy the light bulb is going to spend. But more important for me, at first, is the brightness. I need to have some level of brightness on the light bulb so I can read or I can do something else. Okay? And the brightness of the light bulb, or how fast that energy is being changed, actually is then measured by power. So what really matters for me is power. Okay? Is electric power. Now, let's say this here. Power, by definition, is change of energy or work divided by time. So this is what power is. If we look at our very first equation here, okay, work done by electric force is voltage multiplied by charge. So I can plug this back into my equation for power. Voltage multiplied by charge divided by time. Okay, and we can identify that charge over time is actually electric current. So power is going to be then voltage multiplied by electric current. And this is my, let's say, way to calculate the electric power dissipated in an electric circuit. Now, sometimes I don't know voltage or I don't know current, but I know electric resistance. So it is convenient to express power also in terms of electric resistance. Let's remember that from our definition of electric resistance, R is delta V over I, or delta V equals Ri. And if I get this result for delta V and plug back in here on my first equation, I can say that power is going to be then Ri multiplied by I, or power is Ri squared. And then we have a second equation for power. I could also come from here and solve that original equation for I, delta V over R. And then plug this back into my original equation and have that power is going to be delta V that multiplies delta V over R. And so power is going to be then delta V squared over R. And this is my third equation for power. Usually, when we're dealing with an electric circuit and trying to compare things to get which system is brighter, which system is louder, which system dissipates more or less power, something would remain constant. In a typical household installation, the voltage on the outlets is always the same. In an electric system where the elements are all connected in series, one after the other, the electric current is going to be the same. So what we need to do is identify what quantity remains the same, what quantity am I analyzing, changing, and then I choose the equation for power that combines what is going to be the same and what am I changing to study the relationship. And this then ends my lesson about the introduction to DC circuit. I have just covered what would have been the algebra-based definition of all of these concepts. And now we should work some exercises. In a next lesson, we then will see what the calc-based version has different than this. It's not much, very little actually.